Hello, I'm Dee Dee, and welcome to my talk on the temporal and spatial blooming patterns of 8 UK jellyfish species over a 20-year period. So you might wonder why we study jellyfish. Jellyfish and blooms are natural components of a healthy ecosystem, but they have historically been perceived as a nuisance to humans. The most obvious is public health, particularly if the UK will be seeing an increase of more dangerous things like this Portuguese man of war, which can be quite nasty. Fisheries are also subjected to damaged nets, stock, and with little warning. A bloom incident in 2007 killed over 200 tonnes of salmon, costing over £1 million in damages. Tourism can also be heavily impacted by jellyfish. Israel alone loses out on millions each year due to jellyfish and lost tourism. Power plants can be a big one as well. Jellyfish get caught in the grates, causing partial or total shutdowns. And an example of this happened in 2011, costing the Scottish power plant £1 million every day it was shut down. So here is a brief overview of what my talk will cover. We will be looking at the temporal patterns of jellyfish blooms and population variation over time, and the regional spatial patterns of blooms and their variation over time. My study will encompass all observations, the variations between species, further analysis into regional spatial patterns, and possibly potential links to environmental factors. Here are some quick facts before we get started. A jellyfish bloom is a large increase in population in a short time and a localized space. Jellyfish populations can undergo climatic cycles, however, it's not known which species do this. And previous studies do not encompass enough time to prove or disprove an increase in jellyfish, despite perceptions of the media that they are increasing. This is my study sample, the 8 species that I'm looking at. The percentages indicate the proportions that they make up in my data set as a whole, not just the blooms. You can see that the moon jelly is the most common species in my data set. And this is generally because it's the most common jellyfish in UK waters. It takes quite a lot of work to get raw data from more than 29 different datasets ready for analysis. First, I collected data from both NBN Atlas and GBIF to ensure I could work with the most complete data possible. I cleaned and tidied the data using Excel and R so I could combine both the NBN and GBIF into one big data frame. The next slide will explain further, but I then needed to resplit the data to analyze them separately. After then, they were ready for analysis. So as mentioned previously, the data needed to be split for separate analysis. This is because one dataset from the MCS makes up 67% of my total data and 92% of the blooms data. However, is only encompassed between the years of 2003 and 2015. This can create data deserts on either side, which completely unbalance my data. It's important to note that the non-MCS blooms have a much limited access. This is because there were so little numbers over the time frame. 2012 is comparatively a very low year in all of the sightings, and in fact in the non-MCS blooms there were no sightings during 2012 at all. However, you can see gentle oscillations over time in both of the data sets, which could indicate climatic cycles. The next logical step was to perform a linear regression to assess if blooms are changing over time. So again, we have our 3 graphs here and working to a 0.5 significance level. Starting with graph number 1, there is no evidence of a change over time. and the Shapiro-Wilk test tells us that the data is not normally distributed, and this is likely because of the MCS data offsetting the rest, throwing it out of balance. So moving on to graph number 2, you can see here the gradient is very steep. However, when working to our 0.5 significance level, the data is again no evidence that there is a change over time. However, the Shapiro-Wilk tells us this time that the data is normally distributed, so the lack of significance is most likely due to the decreased time frame in comparison to the other data. So lastly, graph number 3, this data showed an evidence of blooms and in fact a 0.36% increase of blooms over time span. This roughly equates to an extra bloom every 3 years. The Shapiro-Wilk test again confirms the data is normally distributed. It's really important to notice that the y-axis here is 10 times lower than the other graphs, and this is because of the sheer weight that the MCS data has over the non-MCS data. So what does this mean? When the MCS data was removed, the normally distributed data over the 20 years shows an evidence of an increase of blooms, approximately 1 bloom every 3 years. However, it's important to know if this is a true representation of a genuine increase or an increase of sighting effort as a result of the popularity of citizen science. So further investigation is needed. Moving on to the spatial patterns of jellyfish. I used QGIS to look at the spatial patterns of jellyfish blooms. This map here shows the total bloom sightings over the whole 20 years, and you can notice that they tend to be on the westerly coast. These animated heat maps show the change in spatial density over time. The full data set appears to show no pattern. However, the MCS appears to occur predominantly in the southwest quadrant, while the non-MCS data appears to occur in the northwesterly region. To make sure that this isn't representative of locations of increased observer effort, more analysis is needed. These maps show the total bloom sightings over the entire 20-year period for each species. This is to show that there can be spatial variation between different taxa. Some species appear to be heavily distributed, while others tend to bloom in localized regions, such as Velula and Rhizostoma pulmo. Further analysis is needed to assess if this will change over the time. I also want to mention that moon jellies account for over 50% of the total bloom sightings. This is interesting when they only account for 27% of the entire dataset. So, in summary of what we've covered today, numbers of jellyfish blooms appear to oscillate over time, and this could possibly be related to climatic cycles discussed in literature. When normally distributed and measured over the full 20 years, blooms appear to be increasing with time. Certain species are being observed in similar regions over the 20 years. However, further analysis is needed to determine if there is a relationship with time. So what do we do next? In order to understand if these results represent a genuine increase in blooms or just sightings, observer effort will need to be quantified. The analysis of blooms will also be used on all observations to assess if jellyfish populations as a whole are increasing. This will be separated into variations between species, and more detailed time series analysis will be done on species-specific blooms in relation to geographical regions over time. If suitable data can be found, potential links to environmental factors may also be investigated. Thank you for your time. I'm happy to answer any questions you might have.